Hello and welcome back to my lecture series on James space, a topic from functional analysis, or more precisely, Banach space theory. In the last lecture, we proved the central theorem that James space has a monotone and shrinking basis. And this will now allow us to apply everything that we have learned before that. So our theory, especially of isomorphisms with certain scalar sequence spaces, certain spaces of scalar sequences. And if you remember the identifications from part 4, then you will know that since J now has a monotone and shrinking basis, we get the following identifications. J will be isometrically isomorphic to Sj, J dash to S dash of J, and J dash dash to S dash dash of J. One thing to note straight up is that the norm of Sj, so I will now just call these Sj, Sj dash, and Sj dash dash for even faster abbreviation. Now this was just defined as the supremum over the projections over these vectors right here, and En was our basis. In the A norm, and since this basis is monotonic, we get that this is also the limit as m goes to infinity of exactly the same term. And well, this is just the norm of alpha n in James space. So what we see is that these norms are actually exactly the same, and furthermore, Sj is already J. It's not even just an isomorphism, it's a straight up equality. Okay. And the very nice thing now is that this norm right here, this is also the norm of Sj dash dash. We now go over to our first proposition, 3.7, which states that if lambda, this is a capital lambda, which is a isometric isomorphism from Sj dash dash to J dash dash, and this is defined in the following way. It's the inverse of phi from theorem 2.3, which was the isomorphism between J dash dash and this sequence space right here, but it's in the other direction. Now, En will, of course, denote our basis, and we want that this denotes the canonical embedding. And we will define the following vector, E0, to be the constant 1 vector, which is an element of Sj dash dash. And now we will have 4 statements. We will label them A to D. So our first statement is that for all elements from J, we have that if we embed J into its double dual space, then the value of alpha n, or the image of alpha n, it will be the same as the image under lambda. Secondly, every alpha n from Sj dash dash converges in R, since they are real sequences. They all have a limit, and C, J, is precisely those alpha n's from Sj dash dash, such that the limit as n goes to infinity of that sequence is 0. And lastly, the extended basis which starts at E0 and goes to E1, E2, and on, is actually a basis for Sj dash dash. And what we will get equivalently is that this sequence, so lambda of the ENs, which will be lambda E0 and then lambda E1, etc. But we know that lambda E1 is just the same as ij of E1, so this is ij E1, ij E2, and on, is a basis of j. This will just be equivalent. It's for free. Now, before we go over to the proof, I want to make a remark about the striking similarities between j and j dash dash, or the sequence space that we identified it with, and the sequence spaces C0 and C. So just like C0 is a part of C and is precisely those sequences which converge to 0, the same goes for these two spaces. And further down the line, we will see that the isometric isomorphism between J and Sj dash dash will actually look pretty much the same as the isomorphism, which is, by the way, in this case not isometric, between C0 and C. There is actually an isomorphism between them, but it's not isometric. So yeah, I wanted to note that because it's pretty cool. And we will now get to the proof. So first we will prove A. And we know that lambda alpha n, which is an element of the double dual space, is that functional x dash dash from j dash dash, for which x dash dash applied to the coordinate functionals is just alpha n. Now, for alpha n from j, we have that ij of alpha n maps x dash to x dash of alpha n, and thus for all n from the natural numbers, we get that ij of alpha n applied to the coordinate functionals, well, this is just the coordinate functional applied to alpha n, and this is just alpha n, and this is nothing but lambda of alpha n from en dash, from the coordinate functional. And since these coordinate functionals form a basis of j dash, because en is a shrinking basis and this is equivalent, this gives that ij of alpha n is lambda of alpha n. It's just the same functional. Okay, for B, let's take alpha n, a sequence of reals, such that alpha n has no limit, so it does not converge. Then alpha n is not a Cauchy sequence in R, and thus there exists an epsilon greater than 0 and natural numbers Pn and Qn, these are now two sequences, with 1 being equal or less to P1, strictly less than Q1, strictly less than P2, less than Q2, less than P3, less than Q3, and on and on and on, such that for all n, we have that the difference of alpha Pn and alpha Qn is greater or equal to epsilon. This just comes from the fact that it's not a Cauchy sequence. Then, if we define Rn to be the following sequence, P1, Q1, P2, Q2, all the way up to some Pm and Qm for a fixed m from the natural numbers, we know Rn is an element of F, and that the norm of this vector right here, alpha n En, we only sum up to Qm in the A norm. Well, this is certainly greater or equal to 1 over the square root of 2 of z of alpha Rn. This is per definition of the norm, and that's the same as 1 over the square root of 2 of what? Well, of alpha P1 minus alpha Q1 squared plus, and then we get alpha Q1 minus alpha P2 squared plus, and on, up until alpha Pm minus alpha Qm squared, and then we still get the cyclical sum alpha Qm minus alpha P1 squared. And this, of course, all in the square root. That's how it was defined. And then we can, of course, just drop all these terms where Q1 and P2, or maybe Q7 and P8 get compared. And we get that this is greater or equal to 1 over the square root of 2 times m times epsilon squared, and this in the square root, because of this inequality right here. And this is the same as epsilon times the square root of m over 2, which of course diverges as m goes to infinity. And thus we know that alpha n has infinite norm and is thus not a part of Sj dash dash. For C, let's first see that for all alpha n's from the Sj dash dash space, so the scalar sequence space that we identified the double dual space with, and for all of our finite subsequences, we have that 1 over the square root of 2 z alpha Pn is less than or equal to the norm as n goes from 1 to Pm of alpha n En in the Sj dash dash norm. And this is, of course, less than or equal to the norm of the whole alpha n in the Sj dash dash norm. And thus, we know that alpha n in the A norm is less than or equal to alpha n in the Sj dash dash norm. And this is smaller than infinity. So if alpha n goes to 0, then alpha n is certainly part of J. Because that this is finite is one of the conditions that must be true for a sequence to be in J, and the other condition is precisely that it goes to 0. So we get exactly what we wanted. J is made up precisely of those sequences from Sj dash dash such that alpha n goes to 0. Okay. And for D, we see that obviously the norm of E0 is 1, and E0 is actually a part of the space. Now let gamma n be a vector from that space and put gamma to be the limit of that sequence gamma n. And we know that this limit exists because that was B. They all have a limit. Then the limit as n goes to infinity of gamma n minus gamma is of course 0. But this means that if at every index we subtract gamma, this, which is a sequence in n, is an element of James space. And as such, gamma n minus gamma 0 times E0 is in James space. That's just a different way to write this, because E0 is the constant 1 vector. But we know that J has a basis, which is En. So we know that since this vector is a part of James space, that gamma n minus gamma 0 E0 has such a representation right here with regards to that basis. And now we can just pull that over to the other side and get that gamma n is equal to gamma 0 E0 plus this representation. And now we want to show that this representation is unique, because this is a representation when n starts at 0 for, well, that's now called zeta n En, right? And we want to show that En is actually a basis. So this extended basis should have a unique representation. Now I will just cross this out because I will now use the zeta n's and suppose that with this going from 0 to infinity, that these are another representation of gamma n with respect to the extended basis. So gamma n is the same as zeta 0 E0 plus the sum as n goes from 1 to infinity zeta n En. Okay. Well, and then we just pull this back to the other side. So we then know that gamma n minus zeta 0 E0 is the same as this, which is a vector in J, of course. So gamma n minus zeta 0 as a sequence in n has limit 0. And since this has limit 0, we know that then the sum of this representation here must be gamma n minus gamma En. Yeah? Because from this here it follows that zeta 0 is just gamma. This means that the representation is unique, and thus that this extended basis is a basis of Sj dash dash. And because this lambda up here is an isometric isomorphism, this last equivalence here, this is just a gift, like it's Christmas. Okay, and now from this we can show theorem 3.8, which is that J is not reflexive. And the proof will go like this. It will be quite fast. So we will define Q for quotient as the quotient space of Sj dash dash over J. Now we just apply our isometric isomorphism lambda. We get lambda sj dash dash over lambda j, and this is just j dash dash over the embedding of j into j dash dash. So this all fits together. And now we let alpha n, which has a representation of this form here, be an element of sj dash dash. And we consider the following element, alpha n plus James space from Q, and then alpha n plus j is the same as, well, just this representation plus j, and we can split this representation up. So this is zeta 0 e0 plus this representation from 1 to infinity, zeta n en plus j. But this is just an element of j, and as such this is just zeta 0 e0 plus j. And from this it follows that the quotient space Q is a one-dimensional real vector space with basis e0 plus j. And from this follows that j is not reflexive. Now, to find a different isometric isomorphism, we will first develop a different technique to calculate the norm in Sj dash dash. And this will be lemma 3.9. And this will state that for alpha n from Sj dash dash and some indices from our set F, we define y of alpha pn to be the following sum. N goes from 1 to m minus 2 of alpha pn minus alpha pm plus 1 squared, and then instead of our usual cyclic summation here at the end, we just sum alpha pm minus 1 squared plus alpha p1 squared. And here too we put it all in the square root. And as a convention, for m equals 2, we will just say that y alpha pn is 0. Then the norm of an element alpha n, this is the same as 1 over the square root of 2 times the supremum of all zeta zpn's, but also all the y alpha pn's. And still pn will just go through our set F. Okay. This will be helpful for the proof afterwards. We will first prove this. We know that per definition, the norm in Sj dash dash, this is just the supremum as k is a positive integer of the following vector, right? Because we just project this onto this k-dimensional subspace, so to say. Okay, and we will first just look at this without the supremum, and we'll write, for that matter, beta n for exactly this sequence right here. And k, of course, is a positive integer. We now look at the norm of this beta n for itself. So let Pn be some indices Now, if Pm is greater than K, adding more indices to Pn, so maybe a Pm plus 1, a Pm plus 2, a Pm plus 3, and on and on. So we just add more indices to this finite sequence of indices. And doing that will not change, so this does not change the value of Z alpha Pn, because only zeros would be added, and since there already is 1 0, this would not change the norm. Maybe we go back to our little picture. So we have here beta P1, then we have beta P2, and beta P3, and we go further and further, and at some point we go to beta Pm. This is the same as 0, and then it doesn't matter if there are more zeros here, and we then go to beta P1, or if you just straight up go to beta P1. Because, well, this is what we would add, and that will all just be 0. So if we add these zeros, then this difference right here, that would just be what this difference was before, and this will be 0, this will be 0. I hope that's okay and understandable. And the important thing is that this case then reduces itself to the case that only the last element of the Pn's is bigger than K. So Pm minus 1 is less than or equal to K. In other words, only those Pn's are interesting for the calculation of the norm of beta n for which this goes. Pm minus 1 is less than or equal to K. So the norm of beta n is 1 over the square root of 2 times the supremum Z beta Pn, as Pn goes through F, but Pm minus 1 is less than or equal to K. Okay? But for such indices Pn, so for which Pm is less than or equal to K, and Pm is bigger than K, we see that Z of beta Pn, and we will add the square here to make it more easier, this is the sum from n equals 1 to m minus 1 of beta Pn minus beta Pn plus 1 squared plus beta Pm minus beta P1 squared. Now we pull one of these summands out, so this is just the same as from 1 to m minus 2 of beta Pn minus beta Pn plus 1 squared plus beta Pm minus 1 minus beta Pm squared. So this is just this. And then we still keep this last summand, beta Pm minus beta P1 squared. Okay. And since beta Pm is 0, because in this case we decided that Pm is bigger than K, this is the same as the sum from 1 m minus 2 of beta Pn minus beta Pn plus 1 squared plus beta Pm minus 1 squared plus beta P1 squared. And what is this? This is just the y beta Pn squared that we just defined. And if Pm is less than or equal to k, we just add an arbitrary Pm plus 1 with Pm plus 1 being bigger than k, and then we have that Pn, as n goes from 1 to m plus 1, is also, these are also valid indices. So z beta Pn is then the same as y beta Pn. So in this case, we go from 1 to m plus 1. Okay, so n equals 1, m plus 1. All right, and this concludes the proof. And now the grand finale. Theorem 3.10. J is isometrically isomorphic to J dash dash, even though it is not reflexive. This is so crazy. Okay, for this we show that Sj dash dash, which is isometrically isomorphic to J dash dash, that this is isometrically isomorphic to J. And for that we will define omega to be the following map from Sj dash dash to J, and we map alpha n to the following sequence. The first index will be the negative of the limit of alpha n. The second will be alpha 1 minus the limit of alpha n. Then the next one, alpha 2 minus the limit of alpha n, and so on and so on. So we shift the sequence to the right and then subtract the limit of alpha n. And the reason we shift this is so that we can store the limit here, because we will need it later. Clearly, omega is linear and injective. Now, to show that it is surjective, we let beta n be an element in J. Obviously, beta 2, beta 3, and on, so we just drop the first element. This is also in James space. So also beta 2, beta 3, and on, minus beta 1 times E0 is an element of Sj dash dash. And this is because, well, this is just the basis vectors, it's just linear combinations of vectors. And now we can calculate that omega of this sequence right there, so beta 2, beta 3, and on, minus beta 1 E0, we can calculate this to be, per linearity, to be omega of beta 2, beta 3, on, minus omega of, well, the constant beta 1 norm, sequence, not norm. And this is the same as, now per definition, this is just the negative of the limit of beta n, and then beta 2 minus the limit of beta n, then beta 3 minus the limit of beta n, and on, minus, and what does this sequence look like? Well, since it's the constant sequence with value beta 1, the limit is beta 1. And so this has negative beta 1 in the first index and then only zeros after, because we subtract beta 1 from beta 1. And a different way to write this is to just use beta n and subtract the limit of beta n times E0. Yeah, because here this becomes a plus, the beta 1 goes in here, and then it's just the normal beta sequence, but with the limit subtracted everywhere. So this is that, and this limit here is 0 because beta n is in James space. So this is just beta n. So we found our Urvektor. Omega is surjective. And now to find that omega is also an isometry, we will use what we have just developed, this calculation via the y's. So let beta n now be an element from Sj dash dash, and let's denote with L the limit of this sequence, which exists. Consider gamma n to be, well, omega of beta n, and as such it looks like this. We have minus L, beta 1 minus L, beta 2 minus L, and so on. And we let Pn be indices. Classic. Now for n being equal or bigger than 2, we know that gamma n is the same as beta n minus 1 minus L. We just see that. So if P1, our first index, is greater than 2 or equal to 2, we know that Z of gamma Pn squared is just the sum right here. If we now put this in, which holds because all our indices are greater than 2, we get the following sum. Here we have beta Pn minus 1 minus L for gamma Pn. And then for gamma Pn plus 1, we have beta Pn plus 1 minus 1. Maybe I should make this more clear here. This is a minus 1 above the n. Alright, so we have a P, a n plus 1, and here the minus 1. And this also minus L, and this squared, plus, then here we have beta Pm minus 1 minus L minus beta P1 minus 1 minus L, and this also squared. And now all these L's will cancel out, and what we get is this sum. And now I will not go over the very details, but we can now put Qn to be the same as Pn minus 1 for all n in between 1 and m. Then these Qn's are valid indices, and they fulfill that Z of gamma Pn is the same as Z of beta Qn. And for P being equal to 1, for P1 being equal to 1, we know that gamma P1, well, this is just gamma 1, which is negative of the limit of the betas, minus L. So Z of these gamma Pn's has the following form. We now split this sum up again. The first factor is gamma P1 minus gamma P2 squared. Then we get the rest, so we go from 2 to m minus 1, gamma Pn minus gamma Pn plus 1 squared. And then we still have our cyclical sum at the very end. So gamma pm minus gamma p1 squared. Now this is the same as beta p2 minus 1 squared, because we here have just the minus L, and here there's also one in there, and that will cancel out. And in here we have, still going from 2 to m minus 1, the beta pn minus 1 minus beta pn plus 1 minus 1 squared. And here the same applies as here. The negative L from the gamma P1 will cancel out the negative L from the gamma PM, and we here just keep the beta PM minus 1 squared. Now we will perform an index shift in here to get the following. This is the sum as n goes from 1 to m minus 2 of beta p n plus 1 minus 1 minus beta p n plus 2 minus 1 squared plus beta p m minus 1 squared plus beta p2 minus 1 squared. And you see where this is going. Here we just put Qn as Pn plus 1 minus 1, and n shall go from 1 to m minus 1. And also we will choose an arbitrary Qm, which is bigger than Qm minus 1. Then these Qn's are valid indices from our set F with Z of gamma Pn being equal to Y of beta Qn. And with our lemma, we now know that the norms must be the same for gamma n and beta n, since the suprema which are calculated in the A norm of gamma n and the Sj norm of beta n respectively are the same set. So we conclude that the norm of beta n in Sj norm is the same as the norm of gamma n, which is just omega of beta n in the A norm, so in James space. So now we have an isometric isomorphism. This is an esom. And finally, with phi being the esom from theorem 2.3, we then have the following isometric isomorphism: gamma phi going from J dash dash to J. They are isometrically isomorphic. Okay, we've done it. We have shown what we have wanted to show. James space is an actually weird space which is not reflexive and still isometrically isomorphic with its double dual space. It's very interesting, I think. I hope you found it just as interesting as me, and I hope you were okay with little errors that I made or my sometimes badly improvised English. And yeah, I don't know, maybe someday I will upload some other math stuff to YouTube, but This was the project that I wanted to do, and now we're done. We'll see in the future. And until then, I wish you good luck with your studies in mathematics and much fun with mathematics. And yeah, that's it from me. Goodbye.